Welcome to our week on basic models. Last week we talked about basic graphs, and in that week, in the introduction video, I mentioned these two graphs. I mentioned simple interest and compound interest, and we compared the two. Those are really something called models. A model is an equation or a set of equations that's used to predict the future in some area of interest. So, a good example of a complex model is the standard model of the universe. It's basically a big, complicated set of equations that governs how subatomic particles interact with each other. So you can use that information to make predictions about what will happen when you fuse things. There are more simple examples based on physical equations, and then there are other models based on economic equations or economic laws. And there are models that show up in a wide variety of industries. They're used all over the place. So we've already talked about two. We talked about simple interest, which is a linear model, follows a straight line. And we've talked about compound interest, which is an exponential model. It follows an exponential curve or exponential growth. And today I'm going to introduce you to three more models. There are three specific models, but they represent three categories of models. One is quadratic models. We talked about quadratic equations. We know we can graph them with parabolas. Another one will represent cubic models. So that's where the highest power of x is 3. And then a third one will represent rational models. And rational models are models from rational graphs where you either have a vertical asymptote or a horizontal asymptote, or maybe multiple asymptotes. You could even have a slant asymptote. I'll give you a really simple one that we'll look at today. The first of the three models that I want to introduce you to today, the quadratic model, just comes from throwing a ball up into the air. Or in general, something is fired up into the air. If you look this up on Google or somewhere, it would be under projectile motion. So this is a projectile. I'm going to throw it up in the air. This axis is going to represent the amount of time that the ball has been in flight. And then this axis is going to represent the height of the ball. So if I just toss the ball up like this, then as the ball goes up, the time moves forward. And let's say it takes about 1 second for the ball to go up to this height and come back down. Then the parabola would look like this. If it only takes 1 second for the ball to go up and fall back down to a height of 0, then the amount of time it takes to reach this maximum height is exactly half of 1 second. Because this parabola is symmetric, it takes the same amount of time for the ball to go up as it takes to come down. So we know that this max height would be happening after 1 second in that case. So this is our basic example of a quadratic model. It's just tossing a ball up into the air. The second model I'm introducing you to today is a cubic model, and it's the model of a cardboard box. So let's say we're designing a cardboard box. We have a certain amount of cardboard to start out with. So we're starting out with this rectangular piece of cardboard, and then we're going to make cuts in the corners. We're going to make little squares in the corners, and after we cut out these 4 corners, which all have a length, I'm just going to call it x, it's all the same length, then we'll fold up on these red lines and these blue lines. So these flaps will fold up, and on the sides they'll fold up. The top of the box will be open. When you do that, this is the picture that you get. And if this side started out at 10 inches, and then you cut out a length of x here and a length of x here, then you get a side left over, this red length, that is 10 inches minus x minus another x. So it's 10 minus 2x. Similarly, for the long side, you start out with 12, you subtract an x here, you subtract another x here, and so you end up with 12 minus 2x for the blue length right here. For the height of the box, after you folded up all the flaps, that height is just the length of these edges, which we're calling x. And so now we can actually write down an expression for the volume of this box in terms of x. And this is nice because we don't actually have to physically make any of these cuts yet. We can just say, well, what if we cut it at this length? Then what volume will we get? And what if we adjust that a little bit? How would the volume change? It's easy to look at with a model. And so with more complicated models like the standard model of the universe, and maybe you're modeling something like you want to build a nuclear reactor, but you don't want to waste a bunch of money doing a whole bunch of experiments. So you use a computer model that's based on a bunch of mathematical equations to figure out what will happen if we change this or we change that. This is just a baby version of that. So for our model, to calculate the volume of this thing, we just take length times width times height. So 10 minus 2x times 12 minus 2x times x. That gives us the volume. If you multiply that out, this is what you get. You can see the highest power of x would be 3 because when you multiply these parentheses times these, you distribute it or FOIL it out, your biggest power of x will come from this minus 2x times minus 2x, which gives you 4x squared. And then that term times x will give you the 4x cubed out in front. And then you'll pick up these other terms as well. If you graph this, it looks something like this. If you don't make any cut at all, then you can't fold it up at all, so there's no volume in the box. So if x is 0, the length of the cut is 0, then the volume is also 0. But if you actually do make a cut, like let's say we cut 1 inch, then you come up to some volume. You actually get a positive volume. And then if you keep increasing x, your volume will keep increasing up to a point. And then at some point, your volume will start to decrease if you cut too much. If you cut too much out of the corners. And in fact, if you cut out 5 inches from each of the corners, this edge was only 10 inches to begin with. So if I cut out 5 inches here and 5 inches here, I'll have no box left. So if you get all the way up to a length of 5 inches for those cuts, then you have 0 volume again. After 5, the graph doesn't make any sense for this physical situation. You can still graph it, but it just doesn't make any sense for this model. So for our model, we would only care about the values from x equals 0 to x equals 5. Now, you can figure out exactly where this happens. I mentioned last time I mentioned maybe in the homework that to find where this happens, you need to use calculus, so we're not going to do that right now. But if you just pop this equation into some solver online, like Wolfram Alpha or something, it could tell you exactly where this will happen. You could just say maximize this function, and it will tell you where that happens. I'm not going to ask you to do that on the homework. At least I won't ask you to do that on the exam. I might ask you to do it on the homework using a computer system or a calculator. But for the exam, all I really want you to be able to do is take this initial setup, create this model from it for the volume, sketch the graph, and interpret that this only makes sense for values from 0 to 5 for this physical model. The final type of model that I want to introduce you to today is a rational model. And so the example that I've chosen is when you're trying to clean up an oil spill. So imagine that your company that you work for is an oil company, and you've got this big oil spill that happened out in the ocean. The unthinkable happened, and now you guys have to clean it up. And you have to think about how much of it do you want to clean up versus how much money do you want to spend. So the way it works, if you think about it, it makes sense. You can't clean it up 100%. If you spend $0, you'll clean up 0%. So if you graph this with a model, you'll start here at the origin. And if we let the percent cleaned be the x-axis or the horizontal axis, then as you come out towards getting 100% cleaned up, you're going to start spending more and more money, but you're never going to be able to hit 100%. So a typical cost for cleaning up something like this might be somewhere between $2 billion and $10 billion. But $2 billion, the difference between $2 billion and $10 billion might give you a huge difference in how much, the percentage of the oil that you actually clean up. So there has to be some analysis done. To get a good accurate graph of this, you would probably need some data from maybe other people's oil spills, unfortunate oil spills in the past, or maybe your company has already, in its research and development area, has already had some people do some experiments to try to figure out how much this would cost, and you'd make a decision of how much money you want to spend based on how much percentage it would get you. You would want to be as efficient as possible. You would want to clean it up as much as possible, but without spending too much money. So a nice model like this can help you to do something like that. Hopefully from these basic models that I've given you today, you at least get a taste for how they can be helpful. They're extremely useful. So as you go on and you use math in the future, these are the main ways that you'll use it.